Hi guys, welcome to ELEC142 Semester 2 commentary for problem sheet 2. This is part 1. So this problem sheet is all about solving different forms of complex numbers and how to convert between the two, how to perform simple mathematical manipulations. And what we're going to do is, once we're very familiar with these, we're going to use these skills to go on to solve more complicated circuit problems. So questions 1 to 5 are quite straightforward mathematical problems, and as we get down to questions 6 and 7, we're looking at them more in the context of waves and complex signals, and this is more likely the form you're going to come across in potential exam questions. So let's start with question 1. So question 1 asks you to convert the following rectangular complex numbers into polar form and plot these on an Argand diagram. We've got A, B, C, D and E. So for this question, I don't want you to prove how you do it. That's not necessary because we're just looking at different forms here. So you should be able to do this on your calculator. Like I said before, if you don't know how to do a polar to rectangular or rectangular to polar conversion using your calculator, Google for the manual and find out. You will save yourself a whole host of time in the examination. And in the exam, I'm not really interested in your mathematical skills. Well, obviously I am, because you need to do it correctly to solve a problem, but that's not the focus. The focus is on solving engineering problems using the mathematics. So we're making the mathematics work for us. So here are our answers. If you do 2 plus J3, it's equal in polar form to 3.61 at an angle of 56.3. And then I've just plotted the graph down here. What I've actually done is I've plotted them all on the same graph. There's a couple of different ways you can look at this. So 2 plus J3, well, first up we can do it on Wolfram Alpha. Yes, our favourite. Remember though that Wolfram Alpha, you need to convert it from J to I, otherwise you'll get a result that you're not expecting, because it will just assume J is a variable, not the imaginary number. And here we go, you can just see Wolfram Alpha's plotted us a nice little Argand diagram down here, with the real axis along here and the imaginary along here. And it also tells us the polar coordinates, so we can have a check and see, was that what we got? 3.6 and 56.3. So yeah, close enough. Obviously, my calculation, I've rounded some numbers up, so you'll get slightly different degrees. Common question is, how accurate do your answers need to be in terms of decimal places? Well, the answer to that is there's no real strict answer. It depends what you're doing. So for something like this, because this number's quite small, I've done it to 2 decimal places after the decimal point. For the angle, sometimes I'll do it to 1 decimal place, sometimes I'll do it to 2. Use your common sense, but it's not the sort of thing you're going to lose marks for. It's just good practice to get into the habit of. If we look at our Argand diagram, we can see we've got a very similar, we've got the same diagram as we had on Wolfram Alpha. The other thing I wanted to draw your attention to is on Vital, in the useful links section, I've put a couple of useful links, as you'd expect given the name. Here we've got sinusoids in phasor form. So if we click through, this brings us to a web page which you can look at in its own environment if you want to. But this shows us the frequency domain on this side and the time domain on this side. So this is assuming it's a sinusoidal phasor. But what we can also do is we can click and see what our Argand diagram would look like. So what was it that we were solving? We were solving 2 plus J3. So about 2 plus J3 would be about there. So yeah, you can see I've managed to do 1.7 and 3, but you know, have a play and see what you can get. And you see what it looks like on a phasor diagram as well. But it's just a useful tool just to aid your understanding a little bit more, so there's some context to the numbers that we're using. So we've got other answers. 3 plus J6 is 6.71, an angle of 63.4, and the rest of the answers are here. These are all, the top 3 are quite straightforward. Then we've got part D, which is 2 minus J3, so obviously this is going to go in a different direction here. So here's part D down here. So it's negative J, so we've gone this way. And E is actually minus 1, positive 7, so that's in this quadrant over here. Just as an aside note, you can actually see that A and D are the complex conjugates of each other, because A is 2 plus J3 and D is 2 minus 3J. It's not so important now, but we'll be using that a little bit later. So that was question 1. Question 2 asks us to express in the following in rectangular form. So we've given 2 lots of polar coordinates. We've got 2 at an angle of 30 degrees and then 5 at an angle of minus 110. So all we've done now is just converted it using our calculators. That's all you need to do. Just getting you familiar with the process of conversion, because when we do more complicated circuit problems, we're going to have to convert very easily between these 2 forms. The reason we want to do this is because generally it's a lot easier to add and subtract in rectangular form, which is this form over here, and it's easier to multiply and divide in polar form, which is this form over here. So that's why we're having all this practice. So next up, question 3, you're asked to calculate A 2 plus J3 over 3 plus J6. So I've just said now that we want to, when we're doing division, we want to be working in polar form. So what we need to do to solve this problem is we need to convert the numerator and the denominator into polar form. Then we can do the division. So here we go. What this gives us with, I've just done this on my calculator, so 3.6 at an angle of 56.3, and then the bottom is 6.7 at an angle of 63.4. Then you can just divide it. So when you're dividing 2 numbers in polar form, what you do is you divide this section as you would normally, so the magnitudes are just divided as you would, and then for the angle, all you do is you subtract the bottom number from the top number. So that gives us 3.6 over 6.7 is 0.5 or thereabouts, and 56.3 degrees minus 63.4 degrees gives us an angle of minus 7.1 degrees. And that's the answer there. So part B, this time we've got a multiplication, and our number again is in a rectangular form, so we need to convert it into the polar form before we can do the division. Sorry, division, multiplication, there we go. So let's just convert that. So the first part, 1 plus J1, becomes 1.41 at an angle of 45 degrees, multiplied by 3.61 at an angle of minus 56.3 degrees. So this time for the multiplication, all you need to do is multiply the 2 magnitudes. So 1.41 times 3.61 is 5.09. And for the angles, you just need to add them together for the multiplication. So for the division, you subtract them. For the multiplication, you just add them. So 45 degrees plus minus 56.3 gives us minus 11.3 degrees.